And we are live. Welcome, everyone. So, for those of you who will be watching like after the live, basically what I'm trying to do in this session is to create some different RAG pipelines with different chunking and evaluate them. And mainly, the objective is to understand which of the chunking method is actually giving us the most accurate or like the best RAG pipeline in terms of changing the chunking strategies. So just to begin giving you a very simple explanation of how a specific RAG pipeline works. Can I close it? No. Okay. Yeah, I think you can see it, but I will. Oh, sorry. Okay. I think you can see it, but I will zoom it a bit more so that we can talk about this image. This image perfectly talks about how the specific RAG works. So RAG is mainly a retrieval augmented generation. It is the entire method is in the name. It retrieves information from a database and it augments them with an LLM. With some other prompts or with the user queries and stuff. So it augments them and then it's put down to the LLM for the generation part with the information or the context in this case. So it is mainly an LLM. If I like in short talk about why we do RAG, it's mainly because of the LLMs, like large language models have a very to to tackle the disadvantage of large language model. That is, the large language models are very large and becoming larger by each research. So it is very hard for these like 70 billion or 120 billion parameter models to train, and it's very costly and obviously hard. So it's done by big corporations and institutions with access to a lot of GPUs. So it is like it comes down to the point that it's not environmentally uh, like sustainable or like environmentally damaging to run this much of GPUs to produce like burn so much energy in the process. So training once is like acceptable because we have actually a large language model. But if you used LLMs in the past, like even in now, if you use ChatGPTs, but ChatGPTs have been like improving the 4 and everything, so they tend to hallucinate, meaning either you ask or you converse with them on a specific topic and they diverge, or they just straight up give you a wrong answer very confidently. That happens because the LLM does not know how to say no, or I don't know, or or they are not actually updated with the latest information. For example, if the LLM has been trained on the all of the internet on 2021, for example, so it's now 2024. It doesn't know what happened from 2021 till 2024. So if you ask them who is the president now in America, the LLM will not be able to tell you because it is not trained in that specific data. So what's the logical explanation is that year after year you train it with the new data. So again, the cost is adding up. Even the larger the model, and the models are getting larger, so obviously it's like the costs are increasing in a like exponential manner if we want to talk about that. So to tackle this problem of getting reliable information from an LLM, uh, the retrieval augmented generation, or the RAG process or method, has been introduced. So basically what it does, that we have, for example, in our example of an LLM which has been trained on the data of 2021, so we have this extra data from 2021 to 2024, these like 3 years of data. So we have this data in a format, like in a text format or whatever. So we want to have the data somewhere in a database, and then we want to chunk it. Chunk meaning like it is like very like, it's the literal meaning that we like divided it into pieces, and it might be equal pieces, it might be, because there are like different chunking strategies involved. So it is divided into pieces, chunks in this case, and each chunks is converted into an embedding vector. So what is an embedding vector? I think um, to explain you in a very simple manner, embeddings is what machine understands of, like if you give an image in like back in 2016 or 2018, when we used to do like ResNet training, or the simple deep learning AlexNet trainings, those, like when images were given to those networks, they normally converted the image into embeddings, and those embeddings normally explains what the image actually is. So embeddings is normally a vector. It can be a large, like just vector or full of numbers. The numbers we don't understand, we don't actually know what those numbers represents, but if we like LLMs understand what the context of the picture or whatever is using the embedding. So embeddings plays a very important role in this machine learning or deep learning framework. So let's talk about okay. 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 Right. Cool. Okay, so we have an embedding model which embeds each of the documents, each of the chunks in our case, and then store it into a vector database, because these databases normally has a lot of vectors. And why we use a vector? Because it's easier for us to find relevant chunks if we do a simple process, like simple mathematical calculations called cosine similarity. It is a very, if I just cosine similarity is a very, like we learned it in our bachelor's. It is, here is just very simple calculation between two vectors. What it gives you is how close the two vectors actually are. So I can explain it further than the like RAG process, I think, but like that's the main key mathematical equation that we actually use to find out which chunks we would require from this vector database. Cool. Okay, so you have the knowledge base. You divide it into chunks, and like we call it documents in LangChain, or I think Llama Index we call it documents, but chunks. Then chunks are, each of the chunks have a specific embedding associated with them, and then those embeddings, as well as the chunks, are stored in a pairwise manner. Like these are the chunks, and these are the embeddings. These are the pairs, and these are like stored into the vector database here. So now comes the this is the pre-production part. Like this is what we do before the RAG pipeline or the LLM is being used for general purpose. So after each of the documents have been like turned into an embedding and stored into the vector database, we come into the production part where we actually use the RAG pipeline. So first comes the retriever part. The retriever part is simple. We retrieve the relevant documents from the vector databases. How? Firstly, we ask a question. For example, who's the president in the United States in 2024? This might be a query. So we put the query and then we turn the query into an embedding. The same embedding model is used in this case. So what it will do is that this embedding model produces a vector, and this vector is like we find the closest vector to the query vector using the cosine similarity. And when we find we'll find few of them which are fairly close, we either take the closest one or we take the three most closest one. It depends. But if we take just one, the closest vector, and then we take the associated documents with that, we take the vector, the closest vector, and we obviously have the associated corresponding documents with that vector. So we take the documents and we use the vector to match the closest documents, because otherwise it's not possible for the sentence-wise matching is not exactly possible. That's why we converted it into vector, so that we have something to match with. So when we have the most relevant documents related to that, we take the document out, we take the text out, or in this case here it says the top k similar documents. They are top k, meaning k can be a number. It can be 2, 3, 4, 10. So we take the most similar documents or similar vector, and then we take the associated similar documents, and then we produce the context what we want to send to the LLM. So this part is quite simple. So we take the query, the user query in this case. Yeah, excuse me. So we take the user query and the context. That the context contains all of the documents which we retrieved. It can be 1 to 10, like the k number of documents, the contents of the documents in a appended manner. And with the query and the context, we make one prompt on top of the prompt. It can be the user query, below it can be that context, and these makes the entire LLM prompt, and that is the thing we give to the LLM. So now the LLM does not actually have to rely on its own information, because in the prompt we tell that this is the question, this is asked by the user, and this is the context that you're going to work with or find the answer from. So give us the answer from the context. LLMs, especially the instruct models, are very good at following instructions, because those are trained to follow instructions of the users. So when we specify the LLM prompt to actually get the answer from the context, so it does that fairly accurately. So it doesn't have to rely on his false information or the information that it actually has from 2001. It normally finds the answer from the context, and then gives us the answer back. So it is a very fairly accurate method in terms of getting the accurate answers. So this is the entire RAG process in a very simplified manner. Cool. Right. So what are we going to do today? Today we want to make something similar to that, but there are many, I think, Python codes that are readily available which can be used for this. But we want to make our own. But what we want to focus on is that we want to see how different chunking method determines the quality of the LLM answers. That is what we want to see. Cool. Cool. Okay, it's time to ban some of the bots. Ban, timeout, warn. And I don't know why there's a lot of Twitch bots which comes on and to sell some banners or something. Anyways, okay, cool. So that's the main idea behind this today's session. And yeah, one thing that we will be using is, yeah, one thing that is necessary, like even if we create like different like RAG pipelines with different chunking methods, because each of the different chunking methods will be a different RAG pipelines, and we need to evaluate each of the RAG pipelines so that we can quantitatively say that which one is the best. Simple. So for that, we will be using this cookbook from Hugging Face. It has a very like detailed explanations on how to evaluate the RAG model and also create one, but we will not be able to, like, we will not be following this RAG model because we will be testing out different models. So we will be making the RAG model on our own percent. Cool. Okay. Let's see. Right. So let's start here with the project that I want to work on is these, as you cannot see on the screen, but here, if you can see, these are the files which I have from uh, my university. I want to extract these and make a RAG so that the LLM can answer questions regarding these things. But there is this problem that I'm facing. These are this is an image, not these are images. These are not. Okay, cool. Not sure how the images will perform here because for the images we will have to use OCR method, but we will not be focusing on OCR today. It's so let's just delete this. Excuse me. Cool. Yeah. Okay. Delete this. Okay. So we still have around 8, 9 of these PDFs that we have as our knowledge base, and we can like work on it. So basically, for us, we don't actually care about different LLM because like in a scientific study, we only change one variable to understand like the effects of this variable on the outcome. So if we don't want to change the LLM now, we just want to change the chunking method. There are different, like according to thesis, we can choose chunking method. We can choose the choice like different embedding models. We can even have different vector stores. Sorry, not different vector stores, but we can traditionally have different databases. For example, there's a knowledge graph base, like GraphDB, but that's not be like turning it into a vector. So that's another thing that we can look at, but not today, I guess later. Formulation of the query. So these, like, the blue things, these are the, I think these are the things that we can change. But we, in this session, we want to change just the chunking method and see the effects of chunking method um on the generation, not like the generation, more we are more concerned about the retrieval quality, if the correct documents are being retrieved. Yeah, that's kind of thing. So let us go through this cookbook and then let's see what we can do. So normally we'll use an LLM. In our case, we'll use what's the most powerful one? I don't know. Let's try the Llama, Meta Llama, not the 1 billion, but 1 billion model. More like 3.2, 1 billion, 3.2 instruct, 3.2, 90 billion vision. Instruct. I think let's go here 3.1, 70 billion. Look at this one, 405 billion. Damn. I'm really curious how big is the model. Oh my god, I don't think I'll be able to run this. Can I search for that? Llama 3.1 470B inference GPU requirement. Let's see. Oh my god. Requires this much of GPU memory in a 4-bit mode. 4-bit mode, is it quantized? Is there any way to make it quantized? Damn. The GPUs that can run Llama is 8 times NVIDIA or A100. 8 NVIDIA we have NVIDIA A100s, but I cannot actually get 8 of them at the same time. 8-bit mode and 4-bit mode. Okay. Practical challenges. Let's see. Wait. Let's go back here. Interesting. Card. Which model to use for question answer generation? Here they used I think Mixtral. Yeah, Mixtral, because it's external performance, blah blah blah. Mixtral 7 times 8B. That's the one that we have, but I don't want to use that. 7 times 8 billion model. So let's use a 70 billion model. Instead I want 2 is available, 3, 1 billion, 1 billion, 11 billion, 90 billion fission, 11 billion. Okay, 1 2 sorry, 1 3 1 2. Okay, 3 11. No, I don't want the vision ones. 11 billion fission, 1 billion instruct, QLoRa. no, not something 90 billion, but there's a 90 billion in vision models. I need a I need instruct 3 billion now. Let's go 3.1. 3.1. There's $7 billion, 7 billion parameter model of instruct. This is the one that I want to use. Not sure if I have it in my server, but ooh, what? 8B. Did I use the 8B or the 70B? Interesting. I used 8B, I think. Again, the question remains if I will be able to use this. 70B. Let's write 70B inference GPU requirement. Okay. Calculate GPU requirements. GPU requirement for Llama 3.1 70B requirements. Okay, let's see this one.
Welcome to this video.
Hmm. So how can I get the int 8, right? Okay, let's write the int 8. Instruct int 8 is the model. 8-bit precision, endpoints, blah blah blah. Let's see the model card. parameters is fine. Multilingual text is also fine. Okay. Cool. Okay. Uh, hmm. uh, cool. 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 Hmm. Want to use this one. Am I connected to the today is 2024, and I want to say a few things, starting with the evaluation planning with Hugging Face evaluation cookbook. We'll use this guy over here. Model from Hugging Face to generate synthetic question and answers. Yeah. Cool. All right. There was something else I couldn't quite remember. Okay. Okay, let's start with the pipeline. Yeah, let's start with the pipeline. Okay. Start with the pipeline meaning Python. Okay. Let's see what do I need to. Firstly, I think for that I need to have line chain document. Okay, let me see another one. I think I have done it in the past. Coding short generator, knowledge graphs, Perplexica. think that is called apt rack. The rack Sebastian will also work. Yeah, wait. Let him expose. Cool. Okay, let's do some imports. There is this request, Hugging Face embeddings. Have some of these. Okay, so let's start with sentence splitter, directory leader, vector store. X. Okay, let's go here. How are they splitting the documents? Like how did I split the documents here? So extraction from, okay, extraction is the first step. So let's extract the documents. Where is it? Let's keep it here and extraction from code. Okay, so this is the base. Variables. Ah, that's, and then I have the US, then Got 9 files. Cool. And now I have the file path. For file in files, mostly I want to live the path. The path would be this one. Write the files of this, and of course I need tktm for tktm. And from cool. I think that's Yep. Okay, let's create another folder named this one. Okay, and let's start. So what it's doing is basically yeah, sorry. What it's doing is basically extracting the information from the PDFs and turning it into an MD file, and that's the MD file that we will be reading. Okay, cool. So when we have the MD file, for example, here, there's this character level chunking and llama index. There's this lang chain. And what I need to do is that when we transfer into embeddings, and then we have the retriever, vector index, vector index, similarities, that's the retriever. Cool. These things are all llama index core. Okay, cool. I need to find something from the llama index to help with this. Cool. So this is finished. And we have the MD files. Let's open one and see it. Gives an overview, classification of these things, created, change, or not as cool looking now. Okay. Okay. So the plan is to create different vector stores, and then vector stores will have the different embeddings, and then we will basically test on the vector stores the quality index. That's creating the 4 different vector stores, or in our case, how many do I need? Okay, everything's written here. So these are the docs and the chunk size, token base, character level, simple directory reader, loading directory reader, chunk size, overlap is 20, sentence splittings. Same thing, eh? Chunk size. Is it's just the MD file, and then we create some of the things with this thinking. Here there was one called chunking methods in evaluation. Trunking algorithm, recursive text splitter to token text splitter. Cluster semantic chunker, algorithm semantic chunker. Gott dich. Modality specific changes necessary different text images label separately on. Okay, so there could be chunks and chunks with metadata as well, right? literature for different chunking strategies, implementing new chunking methods, summary, embedding, etc. Because summarizing the entire thing can be one. Okay, cool. So let's make one. $20. Okay. Let's so what? These are not even the chunk size, but okay. Let's try the sentence text splitter. Do I need llama or let's see, do I have llama in here? Okay. Llama list, and this is no embedding. Okay, cool. Grab the embedding. Okay. Identic and stuff, not now. Sentence text splitter, cover. Okay, cool. You load the data. It's a directory leader. The directory is actually the empty folder path, and this should be the docs. And let's print out the length of the docs. Should be around. Okay. Hmm. 16. Okay. Why though? That's the question. The empty folders does not have a line, but okay, let's say we have this much of. Go to the variables. Splitter. There's this. Interestingly, because that's the amount of nodes. Oh. What's up with the token text? But if I like, I don't know, just change it to this one, still it's the same, eh? 1626, 1626, just the same thing. What did I do in the other part? So we have this docs, yeah, the document loading, the input directory in our case was the docs, cool, and simple directory reader to load data, that's the docs, and there's this number of files. Lang chain embeddings, not llama index embeddings. Interesting. Go. All of my embeddings, and this should be the okay, we've got the nodes, we have the right, this is the code when latest quarks, don't need this, think find something, and what else, what else? Okay, so once we have the embeddings, I think we can deal with these settings here. Llama index core settings would be the yeah cool. Now for the sentence splitter, that's the splitter. Get nodes from document, that's the node parser. Okay, that's vector store index. This. How do I want to persist this? Vector underscore source. Okay. And inside, the first one would be the sentence text splitter. vector store slash splitter. First 10. Sure, why not? Why not? It's converting into the vector store. I think there will be one in here. Okay, but what does Hugging Face say? You split it and then you have the LLM call it. That's the factoid answers. Critic agents. Building on rack system, yeah. So raw knowledge base, recursive text explorer. Chunk size and Creeper embeddings. Ice is the vector store, Hugging Face embeddings. We have rag prompt and that, yeah, this is the one. Using the information contained in the context, give a comprehensive answer to the question, respond to the question asked, there's a relevant to the context, provide the number of sources. Okay, use the context, and now let's answer this question. The question, this is the context questions and now this is since. Okay, cool. Let's copy this down to our here. Okay. Now Hugging Face Hub, the repo, whatever, the reader model, the reader LLM, some things I want to see on the rag type prompt templates being used. Answer with rag. You provide an LLM. The question, the knowledge base, the vectors to re-ranker. Not at the moment. Final prompt, and you send the final prompt to the LLM. That's that. Okay. Question here is question retriever of index similarities and stuff. Cool. This is a message. Cool. Yeah, let's wait for it to finish. Okay, cool. I think I have some vector stores. And I have the template stuff. Cool, 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 cool. Okay. So let's have the query. Uh, let's open up a PDF and ask from there. For example, it's solidification morphologies in metals. Let's see if it like correctly gives us this things. Yeah, whatever. What is this? This is our query that we can change, and we want to retrieve. We want to retrieve the vector store. That's the vector index retriever. Yeah, okay. So it's retriever.retrieve query. Okay. And the return text. And let's add it here. Okay. This is the example of lang chains vector store. It returns a similarity here. I think top case similarity, whatever. But that's for llama index. So that's the relevant talks. Re-ranker. There's no re-ranker. Filling the final prompt. I've already made the final prompt. History, query wrapper. Where did I? Query wrapper prompt. Context in the question. So that's the text return and the query. Got this one first. This should be the from template, context, and the question in this case would be the yeah, okay, cool. We're not actually sending it by history, rather than that we are okay, now comes the LLM, right? Now do I have to move everything to the server to use the LLM? That's the question. But even though like we have the like final, let's final prompt equals to this one, and then we have this is the final prompt that we will be sending to the LLM. That's it. But we don't actually have to test it with the LLM, but we have to see that the returned text is good or not. That's the one. So let's see. Like 10 it will return, and we will be able to see the final prompt here. But okay, let's try to print it. Final prompt. Constitution. Okay, let's go here. There's a lot. Yeah. Okay. Let's see the text editor. Concentration on the cooling different solidification morphologies. What was the question again? Our question was solidification morphologies in metal, solidification morphologies in metal. Okay. Chapter 1.4 solidification morphologies in metal. Other metals. Is there anything similar to these two things? Because they are getting it somehow. Let's see one thing. Retrieve the query, right? Okay, let's see the returned doc. What's the first one? It's node with score. Embedding none. It is found in the casting technologies. Okay, cool. MD file. Yeah, it is from here. File size, creation date, modified, excluded, file name, blah blah blah. Excluded metadata. Three different solidification processes. Structures. Okay. Okay. Wait. File prompt and get it onto here. Then we can search it. Yeah. Let's search this part. Oh no. Sorry. Copy. Paste. We have it. Yeah, we have it. So, okay, cool. These grains are due to blah blah blah. Okay, the cooling rises, melting. Okay, let's see if we have downward layer. No results. Typically on the metal. No results. Okay, but we do have some queries that are being written. It's not obviously good, but we do have some something that we can use it. So what's next? Next is to benchmark the RAG systems, different evaluation metrics based chat evaluation prompt on factual example results, better reader baseline RAG. It's from test evaluate. Benchmarking the existing. Synthetic data. Okay, synthetic. RAG systems and evaluation datasets now ready. Evaluation datasets are now ready. The last of just the LLM, just the RAG system output on these evaluation datasets. Today we set up to judge on different RAG evaluation matrix, different RAG evaluation matrix. This it is stable version of this documentation. Okay. We choose to focus on the faithfulness since it's the best end-to-end matrix to our system's performance. Cool. For the elaborate judgment. Okay. Evaluation from task description and instruction. Write a detailed feedback that says the quality of the instructions to evaluate the instructions. Response to evaluate response. Rank chain. Your fair evaluator of the language model. Incorrect, inaccurate, and are not factual. Reference answer. This is response. Chat prompt template. Is the response reference answer? Evaluation prompt template equals to chat from template from message system human message prompt template to from evaluation prompt. That's that. That is what we use. Yeah, so the instruction, so the instruction of the experiment question, experiment generated answer, true answer. Okay. The question that generated the true answer, because questions would be the questions that is being also synthetically generated. Cool. So write detailed feedback. After writing feedback, write a score with the integer. You should refer to the score rubric. The output should look at the format, feedback, write feedback. feedback, write a feedback. So from there, I think searching the result, that's the content that eval prompt, invoking the chat model with the eval prompt. That gives us the evaluation result, and from there we get the feedback and the score. We strip the item from the eval result, the content. That's the content, and we split the content with the result, and that's okay. Okay, so that's the feedback and the, of course, that makes sense. That makes sense. Okay, so let's copy this evaluation prompt because we're going to need this to evaluate the faithfulness on how completely is the response correct, accurate, and factual based on the reference answer. Okay, there are other matrices that I want to also see that needs the work of LLM model as well. Okay, which LLM model is being used? That's the evaluation chat model. Chunk size, the chunk size of tokens, re-rank, true or false. Okay, wait, evaluate answers. Evaluation chat model, what is that? What's that? Yeah, and okay, so using the GPT-4 preview from the OpenAI. Okay, cool. So using a fairly big model. Fairly big model. Can use the 70B model. Yeah. I have some evaluations. What else? We put that okay, I have to generate synthetic question answer data sets as well. Okay, let's see if the simple directory to the reader PDF, yeah. Quickest to load data from the local console llama index is most likely blah blah blah. Supported reading files is IPython notebook, CSVs, docs, markdown files, PDF. Yeah, PDF is something that they natively support. So what if I just change it to from the PDF, like I don't know, what was the name? Folder path? Yeah, folder path. And PDF. Let's read it again. have it set up, and we make another vector index storage context persist. It's the vector index, and we store the persist. Okay. How to load persisted vector index in llama index. Persisting and loading data. Storage context. Let's move it here that I can see. Storage context dot persist is persisting the data, and then storage context from defaults doc store equals to simple document store vector store. Storage context is the same. Okay. Doesn't say anything about storing or persisting the data. Remote backend persisting. Persists. Mhm. Hmm. Rag vector store will have the questions. These are the questions, and get the dogs, get answers, run write answers. Storage context is as retriever. Okay, okay, cool. Index from storage. That's true. Index from storage. Self the storage context. Okay, and from defaults, and I give it the persist directory location from where it is normally. Interesting. There's only one vector store at the moment, so I changed the folder path. Yeah, now it's working on the PDFs rather than the MD files. Less number of nodes, and yeah, let's see how it works with the PDF thing. I'm telling it to persist here, context storage and persist, but I can also retrieve it using these three things. Loading the retriever. Store path should be here, and that's the index, that's the retriever, that's no, yeah, cool. the rec prompt, final prompt, and what I can do is print. This is a more comprehensive one because it is dealing with I don't know. Let's see if there's semantic grain structures. There is this part here. No results. Assumptions, mixing. Results. Yeah. No clue why isn't this one's working, but yeah, we have something to question is we don't have specific question answer things. To generate the question answers, we need to have some LLM. Now that we have some different okay, let's think about having a different we can have a different doc systems, different chunking methods, but we can also have, it's called the summarized embedding. We can take a chunk of it, most probably semantic chunk, and then summarize it, keep the embedding of the summarization as well. Can I have a complex vector index with, because these are not really allowing. So it's just, if we have a marked up file here, normally what I'm trying to do is this, suppose these are the entries, and for now it is chunk and chunk embedding. This is the normal, but in here I also want to create what I call chunk summary and summary embedding. So when we just it's not link definition, so it's just the same here. Chunk 1, chunk 2, chunk 2, chunk 1, chunk 1, summary 1, 2, and 2 here. Something along this path. Oh, looks bad here, but somewhere around this line. But that's the question, you see. We need a LLM who can summarize it. We can ask our main LLM to summarize it. We can ask our main LLM to summarize the content, the chunk, and that can be the actual vector index. This can be actual vector index as JSON file or just an L file. I learned there's a new type of file called JSON L online. Let's move everything. Yeah, except for the .env files. So let's create a git ignore. Yeah, and I saved the .env. The project MDs and everything should also come as a sample. The hell is this? What? Anyways, let's create a Git repo so that we can send it. Initialize repository. Initial commit. Prepositions. Rag research. API. Okay, cool. Initial commit, just commit and publish branch as a publish private public repository. Yes. Let's create this files. Oh.